Hi, my name is Miriam Ramos. I work at MPE, and today I will give you the introduction to the eROSITA telescope and its capabilities to map out the large-scale structures in the universe in X-rays. So eROSITA stands for an extended Roentgen survey with an emerging telescope array. It's on board the Spektrum-RG observatory that you can see in this picture, and it also carries another Russian instrument called Mikhail Pavlinsky. SRG was launched in July 13, 2019 from the Baikonur Cosmodrome to the Lagrange 2 point, which is located 1.5 million kilometers away from Earth. As you could have known, it's a German-Russian collaboration, and the expected lifetime of the observatory is more than 7 years. So what is the eROSITA advantages in comparison with other X-ray observatories, like current ones like XMM and Chandra, which have a small field of view that you can see in this diagram of 30 arc-minutes and 17 arc-minutes from XMM and Chandra, while eROSITA has a larger field of view of around 65 arc-minutes. But eROSITA also have another feature, that is the scanning feature. This allows eROSITA to perform, to have 3 observing modes, that is survey, field scan, and pointed, in comparison with XMM, which they only have pointed observations. And this helped a lot to map out the large-scale structures in the universe. For example, in this image, I show you the triple galaxy cluster system called Abel 339195. And in the 90s, it was observed by ROSAT in the first X-ray all-sky survey. But ROSAT had a bad resolution and the sensitivity was not great. So you could see mainly the galaxy clusters, some very bright AGNs. In the 2000s with XMM, which has a very good resolution, but a small field of view, we could only observe with pointer observations the main galaxy clusters in this system. But now with eROSITA, in very few hours, thanks to the large field of view, the scanning feature, and the large perspective area that eROSITA has, we can map out the environment around this galaxy cluster system and understand more about the physics that is around the system, which other objects we can see there, how many large extended sources are around this one, for example. eROSITA has 3 main scientific goals. First of all, we hope to detect and study 50 to 100,000 galaxy clusters and groups. And of course, the hot has filament between the clusters. And this will help us to understand and to study the formation and evolution of the large-scale structure in the universe and to put some cosmological constraints using galaxy clusters. Also, we hope to detect up to 3 million of black holes or AGNs. And having all these observations will also help us to study more in detail the galactic X-ray source population like X-ray binaries and supernovas. And this will be achieved thanks to the eROSITA all-sky survey. Up to now, eROSITA has mapped out the entire sky 3 times and is completed 3 times. So because every all-sky survey lasts for 6 months. So here I show you just an image of the first eROSITA all-sky survey. You can see some of the very large scale structures in our galaxy, like the so-called eROSITA bubbles, these ones in yellow, some supernovas, but also some extended sources in the background, which are galaxy clusters or superclusters. The data policy and data sharing between Russia and Germany is to have the German consortium, eROSITA consortium, to have the right exploitation only on the half part of the sky, which is the one that I'm highlighting here. On its way to Lagrange point 2, eROSITA performs some calibration and performance verification observations, and that's what my colleagues will show you in this eROSITA session. We will start with Jeremy Sanders, which gives you some calibration overview. Then Angie Veronica and Veronica Biffi will show you the observational and simulation point of view of the cluster astrophysics and the large-scale structure. We also perform some observation to test the survey capabilities of eROSITA. We perform the so-called eFEDS survey, and some of the results will be shown by my colleagues Ang Liu, Vittorio Ghirardini, and Emre Bahar. And some forecasts for the eROSITA all-sky survey, especially the weak lensing follow-up and some predictions for the cluster cosmology will be shown by Florian Pacaud and Johan Comparat. Thank you.
Thank you very much for the introduction, Miriam. I'm going to be talking about the eROSITA calibration clusters, and my name is Jeremy Sanders. So the eROSITA calibration clusters are a set of clusters observed by eROSITA to ensure that the observables that we measure with eROSITA, for example, temperature and luminosity, can be directly compared against those from other X-ray observatories. This is really important if we're trying to infer the masses of the clusters measured by eROSITA. I'm going to be talking about 4 different clusters: Able 3158, where Bieber and Wheeler led the analysis; UGCO 3957, where the German lead is Jan Aschersleben; A3408, that was led by Jana Ilan-Karovic; and Able 3266, where I took the lead. So here are some thermodynamical profiles from some of the clusters where we're comparing the results from eROSITA against those from other X-ray observatories. And on the left, you can see Able 3266, where we're plotting the temperature, metallicity, and normalization. And I'm plotting 2 different lines here for eROSITA because we're a bit unsure about what the galactic column luminosity is. But you can see that the temperatures we get with eROSITA are pretty close to those from the other X-ray observatories, somewhere between the 2. And the same picture is also seen in the metallicity and normalization. For this other galaxy cluster here, Able 3158, we're also seeing a very similar picture to that. Pretty good agreement between the different X-ray observatories, although there are some differences in some places. And some of this might actually come from multi-temperature gas within the clusters, where you get different biases because of the nature of the instruments that we're using. We can also infer other quantities from the clusters, such as the hydrostatic mass. And this panel here shows you the inferred hydrostatic mass profile for 3266, where I'm plotting the cumulative mass profile for eROSITA in red, and the dotted line here is for X and M from Ettore et al. And you can see that we get pretty good agreement at the 10% level at this radius, which is around for R500. I'm going to talk a little more about 3266, which is one of the prettiest looking clusters in the sample. Here's a very nice RGB image where we basically split the cluster into different energy bands here. And you can see the really disturbed nature of the galaxy cluster here. It looks a right mess. I'll talk about that a bit more. Surrounding the cluster, you can see AGN, and there are actually some background clusters that I don't have time to talk about. And what's really nice is that R200, the galaxy cluster, fits within the eROSITA field of view, so we can really look to the outskirts. In more detail, if you subtract an average model from the galaxy cluster, this is what you get. So this is the residuals left from the average model. And you can see, this is a kind of schematic that's showing you what's going on. There's a kind of bright region here to the top left, which is likely some kind of subcluster that's merging with the main cluster. You're getting this kind of fan-shaped structure coming out behind it. This bright material here to the west appears to be strip material of another subcluster that's passed through the cluster. And you see yet another subcluster up here, which is likely passed through the cluster. And you can see this by the X-ray contours point towards this subcluster. So there's at least 3 different subclusters merging with the main cluster. You can also see that the edges in the X-ray surface brightness. On the left, you see a map here where I've computed the gradient of the X-ray surface brightness. And you can see changes in the X-ray surface brightness profile at various different radii. For example, around this kind of core region and roughly around R500 out here where you can see this edge. And we can also compute thermodynamic maps of the clusters. So this is some Able 3266 temperature map. And you can see this subcluster here is cool material. It appears as low entropy material. Ahead of the cluster, we also see some kind of high temperature gas, which might be a shock generated by this merger. This thing out to the west is also low entropy, plus this one up to the northwest. So as I said, there are at least 3 different subclusters merging with the main cluster. We also see that the other clusters aren't completely relaxed either, even though on first appearance they might be the case. So this is Able 3158, where it looks fairly relaxed, except you also see, you might be able to see a kind of extension here to the one side. So it looks like the gas has been shifted off to the side. And you also see this in the temperature map, where there's cooler material that's shifted to one side. So it's not completely relaxed. We also see a rather high velocity dispersion for this cluster, which also implies that the cluster might be under some kind of merger activity. Able 3408, 3407 also seems to show that. So here is the cluster. And there's actually a neighboring cluster that sits somewhere over here. This is the cluster itself, 3408, 3407 sits here. And the X-ray appears to be disturbed in that direction. And we also see that there's temperature change. So the gas on this side of the cluster is hotter than that on the other side. So there really seems to be some interaction with the neighbor here. So my conclusions are that these calibration clusters really demonstrate the wide field capability of eROSITA. And we're seeing pretty good agreement with other X-ray observatories who are working to understand and control the differences. Though they're intended for calibration, the eROSITA data really reveal that most of these systems are not relaxed and isothermal. They're great for studying the physics of galaxy clusters and merging systems. And it really shows a potential for eROSITA for studying even larger systems. And this leads on to the next talk by Angie, who will be talking about an even larger structure, Able 339195. Thank you.
Thank you, Jeremy. Hi, everyone. I'm Angie Veronica from the Argelander Institute for Astronomy, University of Bonn. I will be presenting the eROSITA view of the Able 3391 and 95 system. The Able 3391 and 95 system is one of the eROSITA performance verification targets. It was observed in October 2019, and it covers about 15 square degrees of the field, as we can see here in the right-hand image. In the left-hand image, we present the image from the ROSAT All-Sky Survey. ROSAT is the X-ray satellite from the 90s. We can see huge improvement by eROSITA, and actually eROSITA provides us with the deepest large-scale X-ray image of this complex system. In this image, we labeled numerous extended objects in the field with their redshifts. In the center of the image, we have Able 3391 and Able 3395 north and south that has redshift around 0.05. In the outskirts, we notice also some objects that have similar redshift, like the northern clump, little south clump, and another galaxy cluster south of this field of view. Upon further investigation, we also detect 15 megaparsec long filament continuously going from the north to the south, connecting all those objects that has the same redshift. One of the most interesting structure in this filament is northern clump. It can be seen entering the sphere of influence of the Able 3391 cluster, and it has a unique boxy shape. We have follow-up observations by XMM Newton and Chandra to other X-ray instruments. We also use ASCAP EMU radio data and ECAM optical data to study more about this cluster. We identified the boxy shape of this cluster, tail of gas emission pointing away from the main system, and surface brightness jump that is in the head of the infalling direction, indicative of ram pressure stripping as it goes through the sphere of influence of the main system and falling into the main system together with the filament. What we are seeing in this image from eROSITA is a snapshot of large-scale structure formation. And that is one of the eROSITA goals, to detect the large-scale structure. This means that we can expect more of the interesting finding of other large-scale structure in the universe by eROSITA. More interestingly is that this eROSITA view of the Able 3391 and 95 system is in good agreement with cosmological simulation. And that brings us to our next speaker, Veronica Biffi.
Thanks, Angie. My name is Veronica Biffi, and I'm a researcher at the Institute in Trieste and collaborating with the University of Munich. And I'm going to show a few results from cosmological Magneticum simulations that allowed us to support the eROSITA observation of the Able 339195 system. Here, from the simulations, we can actually follow in detail the time evolution and formation of the large-scale structure. As you can see on the right, there is a volume of the cosmological simulations centered on a knot of the cosmic web with filaments and several structures in the center and in the surrounding. And this is the evolution below Redshift 1. In the simulations, by searching for galaxy cluster pairs, we see that we can expect roughly a few tens of pairs per gigaparsec cube that have a mass range for the two members similar compared to the observed Abell 339195 system, so between 1.5 and 3.5 10 to the 14 solar masses, so with a similar configuration. Here, in fact, you can see in the image the direct comparison between the simulation in the central panel over a larger scale of 20 megaparsec per side, compared to the eROSITA field of view, which is on the right, where you see the two main clusters, the northern clump, and here is the filament from north to south. And also in the simulations, we do find very similar configuration, and zooming in to the central part, which covers similar area than the eROSITA observation, we see the two main clusters of the pair, so GC1, GC2, several filaments, filamentary structure, and in blue we mark some gas that is in the interconnecting bridge between the two clusters, which has a different origin with respect to the ICM in the clusters, and it's more filament-like gas. We also have other structures, all showing signatures of volume motion towards the pair, among which this group B on the top right, which is almost merging with GC1, and it's similar to the northern clump. In the following image, you see, in fact, a comparison between the simulated system roughly 3 gigayears ago on the left, compared to the system observed by eROSITA on the right. And you see that the infalling galaxy group, which I named before, is actually entering the sphere of influence of the cluster 1 on the top, roughly at redshift 0.25, so 3 gigayears ago with respect to when we select the pair. And here it already starts to show, together with the other structure in the surroundings, signatures of the motion towards the pair, like sloshing of the gas, significant radial motion, and also some slowing down of the gas compared to dark matter. Further on in time, it will also show signatures of stripping of gas while it approaches more and more the cluster 1. Other than this science that we do with eROSITA PV observations on structures and large-scale structure in the universe, we also were able to test the capabilities of eROSITA in surveying the sky. And Anglu, in the next talk, we talk about more the eFEDS field to show these capabilities.
Okay, so following the presentation of Veronica, I will briefly introduce the eROSITA Final Equatorial Depth Survey, the eFEDS, and the catalog of galaxy clusters and groups detected in the eFEDS survey. So what is eFEDS? Well, eFEDS is a proof of concept mini survey at the depths of the final eROSITA All-Sky survey. And eFEDS is designed to demonstrate the capabilities of eROSITA and also establish and test the data analysis tools. The explore time of eFEDS is about 2.2 kiloseconds and is almost uniform, covering a sky area of 140 square degrees. And the observations of eFEDS were performed in November 2019 during the performance verification phase of eROSITA. The eFEDS field is completely covered with optical surveys and also available at SDSS spectroscopic follow-up and also radio follow-up with LOFAR and the GMRT. So this is the image, the Explorer corrected eROSITA X-ray image of the eFEDS field in the soft band. And we can see that this image is filled with a lot of point sources, which are AGN. And we can also observe many very bright and extended X-ray sources, which are probably galaxy clusters and groups. So we detect in the eFEDS survey about 540 cluster candidates, and we determine the redshift of these cluster candidates with optical survey data. And these clusters span the redshift range from 0.01 to 1.3 with the median redshift at 0.35. And this is the spatial distribution of these cluster candidates. With the eROSITA data, we also perform spectral and imaging analysis of these clusters and measure the X-ray observables like temperature, flux, and luminosity. And the results tell us that the eFEDS clusters are dominated by low mass clusters and galaxy groups. And to better understand the capabilities of eROSITA, we also compute the X-ray selection function using a series of simulations. In the simulations, we include the emission of mock cluster and the AGN from numerical simulations, plus the eFEDS background from the real eROSITA data. And the selection function provides us with the detection probability as a function of luminosity, redshift, and exposure of a cluster, which is shown on the right-hand side. So with this well-understood selection function, we are able to perform further analysis using this cluster sample. For example, we compute the X-ray luminosity function of the eFEDS clusters, and the results are shown here. And we found that the X-ray luminosity function of the eFEDS clusters is consistent with the other recent X-ray cluster surveys. And if we divide the cluster sample into two redshift bins, we find no significant evolution in the luminosity function. And with the redshift information of the clusters, we also perform a systematic search for superclusters in the eFEDS field. And we detect 19 superclusters with more than 4 members. And this is an example where we performed a multi-band study. And this work has been published in a recent paper. And this is another example with the most cluster members. And this is another supercluster with the interesting bullet-like structure and 2 tails at the same redshift. And all these results, including the cluster catalog and also the supercluster catalog, will be published very soon. And there are a lot more works about eFEDS clusters in progress. And next, I will hand over to Vittorio Ghirardini to share with you some interesting results about the morphology of the eFEDS clusters.
Thanks, Hank, to this very nice introduction on the eFEDS field. Now I'm going to explain what are the morphological properties and how they can be exploited for our goals. One of the main goals of eROSITA is to put time constraints on the cosmological parameters using galaxy clusters. However, in order to do this, it's important to use and build a clean and well-understood cluster sample. And using information on these morphological properties is a very good way forward in this direction. In particular, it was shown in Luisa et al. 2020 that if you divide the cluster population between relaxed and disturbed, this helps in reducing the scatter between mass and observable, and thus helps improving the constraint on cosmological parameters. In this work, we measure 11 different morphological parameters. Each of them is valid at different scale. In particular, here in these images, you see how 4 of these parameters can be visualized in X-ray images of clusters. You see here opposite cases for central density and concentration, which are 2 parameters that are mostly related to the core properties of clusters. In particular, they tell how dense is the cluster in the core and how concentrated is the surface brightness emission. P4 0, the 3rd parameter that is listed here, is one of the power ratios and measures the fluctuation level on the cluster images. As a last example, in the 4th row, you see the photon asymmetry, which measures the deviation with respect to spherical symmetry of the clusters. This cluster on top row can be classified according to these morphological parameters as disturbed, while the one on the bottom can be classified also using the morphological parameters as relaxed. This cluster sample that is recovered using the eFEDS observation is very unique. In fact, the luminosity and redshift range that is covered by this sample is the largest that has ever been studied, and therefore we're able to constrain at the same time luminosity and redshift evolution of the morphological parameter, which can therefore be taken out of this analysis. Using these corrected morphological parameters, which are luminosity and redshift independent, we can build a new morphological parameter that is used here in this work for the first time, which we call the relaxation score. This parameter summarizes all the information contained in all the other parameters, taking into account their mean and their correlation and also the strength of the correlation, and is quite useful in discriminating between relaxed and disturbed clusters. Here to the left, we list for completeness all the morphological properties that are studied in this work. To the right, you see the parameter distribution for 4 of these parameters. Since they measure relaxation at different scale, some of these parameters will be quite well correlated with each other, while others will likely correlate or have correlation value close to 0. When we use the luminosity and redshift corrected morphological parameters, as I've explained in the previous slide, and we color code the points according to the relaxation score, you see how this relaxation score separates quite well relaxed and disturbed clusters. As expected, large concentration and large central density and low power ratio and low photon asymmetry indicate that cluster that is relaxed, and vice versa. To conclude, I will present with a few results. So as one result that we find is that the morphological parameter distribution prefers a single peak distribution over a double peaked one. Therefore, this indicates that the transition from relaxed and disturbed cluster is smooth. Furthermore, when we study the evolution of the fraction of relaxed clusters and disturbed clusters, we find no evidence for any evolution with redshift, indicating that the fraction of cluster that is relaxed at low redshift and high redshift is constant, indicating that relaxation fraction does not evolve with cosmic time.
Hey, I am Emre. I'm a PhD student at the Max Planck Institute for Extraterrestrial Physics. In this section, I'll be presenting our work on the scaling relations between the observables of clusters that are detected in the eFEDS field. Scaling relations are simple power law relations between observables of clusters. These relations are shaped by the cosmic evolution of clusters, where the gravitational collapse plays the most important role. Baryonic effects also play a non-negligible role, which alters these relations and therefore make them require calibration. It is worth calibrating these relations because they are one of the most useful tools for cluster science, since they provide a way to convert an observable to the other. Moreover, they have important cosmological applications, since they provide a way to measure masses of clusters from observables that are easier to obtain, such as luminosity. For example, you can see from the figure on the right that there is a clear correlation between X-ray luminosity and total mass of the clusters. However, you can also see that there are many different best fitting results. That is a clear sign of the need for a better calibration. eROSITA cluster group has a partnership with HSC, which came in handy in particular for our eFEDS analysis, since eFEDS has a large overlap with the survey area of HSC. We made use of this by measuring weak lensing masses of eROSITA detected clusters and calibrating weak lensing scaling relations for the sample. The calibrated count rate versus weak lensing calibrated mass relation and obtained R500 measurements of the eFEDS clusters, from which we extracted X-ray observables within this radius. We then used these observables to calibrate scaling relations between X-ray observables and cluster masses. Besides calibrating relations between X-ray observables and cluster masses, we also calibrated scaling relations between X-ray observables. In this work, we are investigating the relations between X-ray observables such as Lx, Lbol, T, MGAS, Yx. We are doing this calibration by running Markov-chain Monte Carlo simulations with a likelihood that takes into account the intrinsic scatter of the scaling relation, measurement uncertainties, selection effects, and the mass function. Now, I will briefly show you two of our results and leave the stage for my colleague Florian to talk about some of our plans for the Old Sky survey. LXT relation is probably the most studied X-ray scaling relation, since luminosity and temperature are the two main X-ray observables. Here, you're seeing the X-ray luminosity and temperature measurements of eFEDS clusters. Luminosities and temperatures are well constrained for most of the clusters. However, temperature error bars of hot clusters are large due to low sensitivity of eROSITA at the hard X-ray band. Nevertheless, it can be clearly seen from the corner plot on the right that the fit is good and the parameters are well constrained. Our results is consistent with the ones in the literature, which is significantly steeper than the self-similar scenario. And in here, you can see that the fit is also good for the LX-YX relation, and the parameters are also well constrained. It is also consistent with the previous results, and it's slightly steeper than the self-similar case. To sum up, our scaling relations are consistent with the ones in the literature, and they prove that the eROSITA is capable of calibrating these important relations. Thanks.
Thank you, Emre. My name is Florian Pacaud, and I work at the Argelander Institute for Astronomy from the University of Bonn. With my talk, we'll now switch to a slightly different focus to describe our plans for the exploitation of the first eROSITA All-Sky Survey, eRAS-1. And in this contribution, I will describe how we intend to calibrate the galaxy cluster masses using weak gravitational lensing. Now, weak lensing implies the need for supporting optical datasets in addition to the eROSITA observations. And we are in the fortunate situation that the eROSITA exploitation coincides with the public release of several major large-scale optical surveys dedicated, among other things, to such lensing studies. This is illustrated with this sky chart in equatorial coordinates, where the red hashed area corresponds to the Russian side of the eROSITA sky, which is not accessible to us in Germany. And the other colors indicates the optical datasets that are of relevance to us, and in particular, 3 of them. So first in cyan comes the wide survey from the HyperSupremeCam Subaru strategic program, which has already been used for the analysis of eFEDS, as you have seen, and contributes 700 square degrees in the German half of the sky. Then in blue is the footprint of the dark energy survey, or DES, which will provide another 4,000 square degrees. And finally comes the kilodegree survey, or KIDS, for a total area of 1,100 square degrees, shown here in yellow. Now, a nice aspect of these 3 data sets is their complete complementarity in terms of depth, sky coverage, and observing bands, but also there are significant overlaps, which will allow for the required cross-calibration checks. So for example, in the case of HSC and KIDS, the overlap amounts to 500 square degrees, shown here with the red boxes. And it also includes most of the eFEDS field, shown in light yellow, where we have deeper X-ray data for detailed checks. In addition, 400 square degree overlap between KIDS and DES is also available, as indicated again with a red contour. Finally, the green color in the chart indicates the footprint of the Euclid-wide survey, which unfortunately will not yet be available for the analysis of the eRAS-1 sample. Now, of course, dealing with such a large amount of data is a significant challenge for which we have set up a dedicated work package within eROSITA. And this is an effort led by Thomas Heiprich from the University of Bonn. So in the work package, our overall strategy is to take advantage of the expertise already gathered within the survey collaborations and mostly rely on it. This is implemented through the appointment of data task leads belonging to each individual collaboration and who are in charge of providing shear profiles at the position of eROSITA cluster, but also quantifying all relevant data-related properties and systematics. For HSC, these leads are Inon Chu and Nobuhiro Kabe. For DES, the lead is Sebastian Grandis, and for kids, Florian Kleinebray and Tim Schrabak are co-leads. Unfortunately, with these data sets, we still don't have enough deep data for a sufficient number of high redshift galaxy clusters. And therefore, we also need to complement them with a dedicated with lensing follow-up for clusters with redshift above roughly 0.7. Here again, we decided to benefit from expertise already in place with a similar follow-up organized by Tim Schrabak within the South Pole Telescope collaboration, which relies on HST and 8-meter class ground-based telescope for the observations. So our plan is to expand the sample of about 60 SPT selected clusters, which will all be part of the eROSITA sample to form a complete sample. Of course, there is still a long way between shear profiles and a full mass calibration that is accurate enough for cosmological application. So for this step, we have set up a common framework for systematic correction across all datasets, and which relies on the method proposed by Sebastian Grandis and Sebastian Bocke in a recent paper. The starting point for this is dark matter simulations, from which the most robust halo mass functions can be established. And a library of simulated clusters with varying halo mass and redshift is first constructed, and each is associated with their counterparts in MHD simulations using the same initial condition, but different prescriptions for the gas and subgrid physics in order to take into account these effects. And in our case, we rely on the Magneticum simulation performed by Klaus Dolag and collaborators. Now, for several projections, and several contributions from large-scale structures in the simulation, the shear profile expected from a given dataset can be emulated, taking into account also the properties of the data themselves, like the miscentering of eROSITA detection or multiplicative shear bias of the optical survey. From there, a common profile fitting method is used to estimate an estimated weak lensing mass, which in turn can be compared with the initial mass function halo mass. And in this way, we can estimate mass and redshift dependent bias for each optical survey, as well as the scatter around it, and also systematic uncertainties on these quantities. And this will provide the link between all eROSITA observables and the halo mass through our weak lensing measurements. Finally, our mock program also comes with a wide range of validation processes to ensure the robustness of our analysis. And this comes in essentially two ways. The first one is to validate cluster scaling relation fitting algorithms on simulated observables. And for this, we'll generate realistic samples, starting from a halo mass function again, and using the first pass of the bias correction framework to simulate realistic shear profiles. And then to each halo will also be associated X-ray observables from eROSITA using a sophisticated simulation chain set up by our colleagues at MP, Joan Comparat, Riccardo Seppi, and Jacob Idachitam. And applying our fitting algorithm to these joint datasets will provide us with measured scaling relation, which we can compare for validation with the link between eROSITA observables and halo mass pertaining to the simulation. A second aspect, of course, is to cross-compare the different optical datasets, and this can also be done in two separate ways. The first direct route would be to focus on eROSITA clusters in common between two optical surveys in the overlap regions and derive their weak lensing mass and bias corrections and compare the recovered halo masses. This provides us with the first sanity check, but unfortunately, the low precision on individual cluster masses remains a limitation. And therefore, we will also consider complete samples drawn from any two optical surveys, either in the overlap area or over the whole sky, and use the two optical data sets separately to measure sets of constraints on scaling relations, which can then be compared. So as a summary, combining all these data sets and tools, we expect to obtain an accurate and robust mass calibration for the ERAS-1 galaxy cluster sample. And now Joan Comparat will take over and explain how such well-calibrated eROSITA samples can be used for cosmological inferences. The stage is yours, Joan.
Hello, my name is Joan Comparat, and to continue this talk, I will now present you a cosmological forecast using galaxy clusters to be detected by eROSITA. To put strict constraints on the cosmological model using a hollow mass function experiment or cluster count experiment, jointly with its clustering statistics, the two-point correlation function, we have developed a forward model of the eROSITA large-scale structure experiment. eROSITA will detect AGNs and clusters, and we have devised in Comparat 2019 and 20 two empirical models of AGNs and clusters so that the cosmic web we have to reconstruct, we can determine accurately how and with which method we do it. On the left side, you have simulated photons of AGNs circled in blue, clusters circled in red, and stars in green. The goal of this experiment is to turn these 2D photon maps into a 3D large-scale structure map. Here you see up to redshift 0.25 and here up to redshift 0.8, all the clusters that have gone into these photons and all the AGNs that have created all these point sources. With the simulations, the first item we calibrate is the detection function and the redshift window. As for clusters with a high flux, a detectable flux greater than 4 × 10⁻14, with an exposure time of the order of 2 kiloseconds, the average eROSITA exposure time, we get for clusters with more than 40 counts a completeness of the order of 80% and a spurious fraction of order of 2%. This is a fantastic figure. This is extremely good to do mass function experiments. The second window function we have is the redshift window function. Using RedMapper-like software, eROMapper, we can determine the effective survey area on the y-axis as a function of redshift. For each of the survey we use to determine redshift, using the red sequence technique, you can see its different reach. In particular, you can see that the legacy DR9 provides us with extremely large area, the full area up to redshift 0.7, and then the area decreases slowly up to redshift 1. If we decrease the requirement to have many galaxy members, then the area extends further out to redshift 1.1. Altogether, we can make a forecast, and you will find these details in PDP 2018, that with ERAS-8, the final eROSITA data, we will get a figure of merit in the dark energy plane of about 70. Together with Planck, it goes up to about 100, and together with BAO and supernova, it goes to 150. So this optimistic forecast shows that on face value, the figures of cosmological constraints on the model are very good. On the right panel, you have a tentative prediction on sigma 8 and omega matter plane of the constraints we will get in 2023 using, in part, eROSITA and SDSS5, and in 2025 using eROSITA, SDSS5, and foremost follow-up. These constraints amount to few percent constraint on omega matter and sigma 8. So we're very excited about the future cosmological constraints. With eROSITA, cluster cosmology enters the precision era. The challenges to complete are selection function challenges and mass calibration challenges. In the coming years, you should expect standalone cosmology constraint from clusters at the 1 to 2% level. Hopefully, we'll also be able to constrain at using high redshift clusters the possible scenario of early dark energy.
Today, we have presented our first exciting results from the calibration and performance verification program of eROSITA. We have demonstrated the power of eROSITA in studying the microphysics of clusters of galaxies, mapping the large-scale structure, and cosmology. Thank you very much for listening. We are happy to answer any questions you might have.